All right, let's get to some vocab. So first off, we're going to look at these three words: a thermodynamic system, the surroundings, and the boundary. Right, so a thermodynamic system. What is a thermodynamic system? It's basically the space or matter being studied. So let's look at this very simple diagram. This is my system, right? So if I'm analyzing the system itself has a boundary around it, right? A mass or region outside of the system. So I'm sorry, the surroundings is the mass or region outside the system, and then the boundary separates the system from the surroundings. It's very important in thermodynamics to define your boundaries. So I get some people say like, well, why is it that important? Because when we do, if you guys think about it, when you're going to be doing problems for this class, the tendency is just to jump right to the equations. What equations do I need to get the answer in order for me to get the 100 on the homework or to get this homework done? And if you guys go through that mentality, it's going to be very frustrating for you. You need to take a systematic approach to solving these. And we're going to go through the same approach as we go on. But one important aspect of the approach is making sure you define your boundary, your system, and your surroundings. We're going to go over an example of why this is important a little bit later. But for example, if I'm studying, I don't know, let's say a classroom, right? I have a classroom. And in that classroom, I'm trying to define the amount of heat traveling from outside to inside. Well, energy is only recognized at a boundary. So I have to define the boundary of the classroom. So I might say, okay, well, the four walls, the ceiling, and the floor define the boundary of the system so that I can look at the energy crossing the boundary, right? So that's important. If this is a potato, for example, and the potato is cooling down, it's giving up energy to the surroundings in the form of heat as it crosses the boundary. And I can't define my heat transfer value unless I define the boundary. So it's very important that you define your boundary, your system, and your surroundings before you even start the problem. Okay, there's different types of systems. Okay, basically there's two. There's a closed system and an open system. So let's look at this example of a closed system. A closed system consists of a fixed amount of mass. Mass, and this is the important thing, you must understand this, mass cannot cross the boundary of a closed system. So here's an example of a closed system, right? I have a piston. This is my piston cylinder assembly. I have my piston cylinder assembly where energy can cross the boundary, but mass cannot. So no matter how much this piston is moving down or up and compressing the air inside the system, the mass is constant. Not the volume, not the density, but the mass. If I have 1 kilogram of air inside of this, no matter what is happening to it, the mass is always 1 kilogram because mass cannot cross the boundary, so it can't lose or gain more mass. All right, just make sure you understand energy can cross the boundary, but mass cannot. And as you can tell based on this example, volume does not have to be constant for a closed system. There's a special case of a closed system called an isolated system. An isolated system is a closed system that does not have any energy leaving or coming into the system. So the mass is constant, the energy is constant, and the volume is constant. So usually the question I get is, well, if that's the case, what's an example in real life of an isolated system? For example, if I have a tank, right, a tank that is insulated. So these little slash marks are my notation for insulated. No heat crosses, right? If it's perfectly insulated, there's no heat crossing it. The tank has a fixed volume and a fixed mass and there's no work being done on the tank. This would be an example of an isolated system. All right. All right. So let's move on. The other type of system, so there is an open system. So there's a closed system and an open system. An open system is basically just an arbitrary region in space. And the main difference between an open system and a closed system is that mass passes through the boundary of an open system. So let's look at this example of a nozzle. Okay, a nozzle Basically what a nozzle is, it's a device that's used to accelerate a fluid, right? You may have seen nozzles, your garden hose, if you have a handle at the end of it, right? In order to spray the water, that would be an example of a nozzle. So here's a nozzle. I have a larger, it's like a cone shape, right? And I have a large area coming in and a small area going out, right? And so if air is coming in, it'll be at a faster velocity exiting than it is coming in. But as you can tell, mass is crossing the boundary. So therefore, it's an open system, right? So not only can energy cross the boundary, energy can cross the boundary, but mass can also. And the surfaces can be real, or the boundaries can be real or imaginary. And I usually get some confusion, like, what do you mean a boundary can be imaginary? So if you look at this, if these lines here represent the surfaces of the cone, right? This exit, if you notice, there's really no surface here at the exit, but the boundary can be defined as the plane of the exit, and the entrance can be defined as the plane of the entrance, right? So it's basically an imaginary boundary. But the boundary is important to define because that is where we're going to define energy. Energy is going to cross the boundary, and we can't know how energy is interacting with the system unless we know what the boundary is. Okay. So here's an example. Let's check this out. What kind of system is this, right? I have a piston cylinder assembly, right? I have this piston that's moving up and down, right? So it's expanding, compressing, expanding, compressing, expanding, compressing, right? So that shows that how my system is doing. But here, if this entrance represents sort of like a valve, I have air entering and air leaving during the whole processes of the piston moving. This would be an example of a control volume, or what we would call an open system. The term control volume and open system are interchangeable. Okay. So now that we've sort of defined systems into two different types of systems, we have closed system and open system, we're going to have to go ahead now and just sort of explain the concept of properties. What is a property? Right? A property is any characteristic of a system. So an example of a property is temperature, pressure, and volume. Those are properties. Those are numbers that you can get that can describe the system. There's two basic types of properties. There's intensive and extensive. An intensive property is independent of the size of the system. So that basically means like temperature, right? If I have a piece of steel that weighs 100 pounds, that's at 50 degrees, and I have another piece of steel that's at 1,000 pounds and it's at 50 degrees, it doesn't matter how big it is, it's still 50 degrees. Density is the same thing, it doesn't matter in the size, right? Pressure doesn't matter in the size. Extensive properties, though, do depend on the size, right? So mass, if I have a 50-pound piece of steel or a 1,000-pound piece of steel, it's obvious that they have two different masses, right? And volume. Volume as well. Volume, if I have a big thing or a small thing, I mean, obviously the bigger one has more volume, so it depends on the size. And also total energy. If I have a hot piece of steel that's 50 pounds and a hot piece of steel that's 1,000 pounds, well, there's more energy in the hot piece of steel at 1,000 pounds because there's just more of it. So because there's more of it, there's more energy. So those would be extensive properties, right? So those are important to know. The real takeaway from this slide, though, is the word specific, okay? So in thermodynamics, we're going to be using specific properties a lot. What does that mean? Anytime in this class that we use the word specific, it means per mass. Extensive properties are per unit mass. So for example, specific volume. That would be volume per mass. Or for example, meters cubed per kilogram. Specific energy. There's several properties that are in terms of specific energy that we're going to look at later. That would be, for example, kilojoules per kilogram. Why are specific properties so important? Because we're going to be looking later in the back of the books for the thermodynamic tables. Those thermodynamic tables have numbers that describe properties of a system, and they're going to be independent of mass by making them specific. So it'd be listed, for example, that this specific substance has a specific energy of 5 kilojoules per kilogram, right? So if you just take the mass, multiply it by the specific energy, you get the total energy of the system. So again, the word specific means per mass. Okay, so I mentioned the word specific volume, and that might be the first time a lot of you have heard it. I take it that you have heard of density, right? Density is just mass per volume, meters cubed per kilogram, for example. In this class, we will use density a little bit, but we're going to mainly be using specific volume. Why specific volume? In thermodynamics, this is a property we use called specific volume. It's the inverse of density. It's volume per mass, right? It's very important to understand that because it is going to be a property that we use very often in this class. There's 6 basic thermodynamic properties, and one of them is specific volume. I'll be going over the other properties at a later time. Something worth mentioning that we're not necessarily going to use is relative density or specific density. It's basically a parameter that looks at the density of something versus the density of water, assuming the density of water to be 1,000 kilograms per meter cubed. For example, if I have glycol and I say my glycol has a specific gravity of 1.2, it just means that its density is 1.2 times more than water. But the real takeaway from this slide is specific volume.